So we've already dealt with geometric series and the general form of them, that we have some ratio that we're multiplying by, and we start at a certain value that we call a, and our geometric series traditionally looks like sum n equals something to infinity, sum a sub n, x to the n. And we already know what the sum of that is also. We say that it's, in this case, it'd be a sub 0 since I'm starting at 0. It's always that starting amount over 1 minus the common ratio. And we're going to expand that knowledge to our work with power series, because there's some power series that we say are in geometric form. And if we can manipulate them, it makes our work really easy. So before we do that, we're just going to kind of refresh our memory a little bit with geometric form, and then we're going to introduce that to some power series. So first of all, let's suppose I have an a sub 1 of 2 and a common ratio of 3. And what geometric series would you write? All right, well, we would have n equals 1 to infinity, 2 times 3 to the n. Nice and easy. And if I wanted to know what the sum of that is, I'd have to say that that is divergent as the absolute value of r, which is equal to the absolute value of 3, which is equal to 3, very redundant I know, is greater than 1. But when we get to our power series, that common ratio is going to have some x's in it, so this whole statement right here becomes pretty powerful for considering what we call our interval of convergence. I'm going to change this one, and let's suppose that's at a negative 1/3 instead of a negative 3, because otherwise that one diverges as well, because the absolute value is greater than 1. So let's do that same n equals 1 to infinity, 2 times negative 1/3 to the n. Again, I'm recognizing this as geometric. I've put it in geometric form. This would start at 2, and then I would multiply that by negative 1/3 every time. All right, so what is my sum of that one going to be? It's a sub 1, or the very first term generated when I put the first count in. So be careful for that with that, because on this one, my first one is a 2, and if I'm starting this at 1, I would have negative 2/3 over 1 minus negative 1/3, and I would determine my sum. Well, let's extend this a little bit more. What now if I have an unknown common ratio and we say that it's x? How would I write that in geometric form? Well, it's going to look like this. It's going to be the sum, n equals 1 to infinity, of 1 times x to the n. And let's even start that at 0. And what I'm going to get with that one is 1 plus, and I'll multiply that by x, and then I'll multiply that by x, and then I'll multiply that by x, and I'll continue. And what I get is x to the nth, and then I'll continue. And what I have right there is a geometric series. But now watch what it converges to. Actually, I'm going to hold on that, and I'm going to go down here just for a moment. We're going to go back up there and write what that equals in just a minute. So put a little box right here. So now it says to find the power series for 1 over 1 minus x with centered at 0 by using Taylor's rule. Remember, Taylor's rule is as long as I have an infinite amount of derivatives at the center, I can generate the series by doing f of x equals 1 over 1 minus x is going to equal f of the center plus f prime at the center times x minus the center to the first over 1 factorial plus f double prime at the center times x minus the center squared over 2 factorial plus f triple prime at the center times x minus the center cubed over 3 factorial plus dot, 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 and then the nth term, f to the nth, derivative, f of c, and then it's x minus c, in this case c is 0, to the nth over n factorial. And on each of these, I'm being centered at 0. All right, so if I were to generate the power series for this using Taylor's rule, I'd have to go and find each of these coefficients. And when I do that, I have f of x is equal to 1 over 1 minus x. F of 0 will be 1. F prime of x is going to equal 1 minus x to the negative first derivative, which is going to be a negative 1 times 1 minus x to the negative 2 times the derivative of the guts, which gives me 1 over 1 minus x quantity squared, and at 0, that's also going to be 1 when I put in a 0 for x. And this is laborious, and that's the whole reason why we're going to try to generate a power series for this in a second. But this is a good review of Taylor's rule. So I'm going to keep going here with it out to 3 derivatives. So f double prime of x, and again, this would be 1 minus x to the negative second, would be negative 2 over 1 minus x cubed times the derivative of the guts is negative 1. So that's going to give you a positive 2 on the top, and when I put in a 0, I'm going to get a 2. So this is going to be 2 times x squared over 2 factorial, and then I'll do one more. All right, and my third derivative at x, and again, this is really 2 times 1 minus x to the negative third right here. So it's good to see the powers when you're taking the derivatives, is going to be negative 6 times 1 minus x to the negative fourth times the derivative of the guts, which is negative 1, which will make that positive. Furthermore, at 0, f triple prime of 0 is going to equal 6, which is 3 factorial. So this ends up being over 3 factorial plus, and that's going to continue to happen, and I'm not going to take that out anymore. And what I'm going to notice is, I forgot my x on this first term, sorry about that. So what I notice here is these are going to cancel. If I continue taking the derivatives, that pattern is going to repeat itself. So I end up with my f of x, which is 1 over 1 minus x, appears to be 1 plus x plus x squared plus x cubed plus the nth term plus dot, 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 which equals the series as n goes from something to infinity, x to the n. And if I want this to start at 1, I have to have a 0 there. Okay, so is there an easier way? And that's the whole point of this. And the answer to that is yes. For part B, it said to do this by manipulating a geometric series, and this is what we're concerned with today. So I want you to go like that. I'm going to take my function 1 over 1 minus x, and what I'm going to do with that is write it as a geometric series. And I'm going to recognize that this is really a over 1 minus r. And what that gives me is this would have a common ratio. This would be the sum of the geometric series that started at 1 and got multiplied by x, that's the common ratio, each time. Oops, sorry. Plus dot, 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 and you'll notice I get that exact same expansion that I got up here, and that was a lot quicker. Again, what I'm noticing is that this is in the form a over 1 minus r. So it has to equal some geometric series. And the geometric series that it equals is n equals 0 to infinity, starts with 1, and multiplies by x every time. Kind of cool, right? Anyway, that was a much quicker route. The third way using long division also will generate this same series. So first of all, I generated it using Taylor's rule, which was quite laborious. Then in part B, I'm recognizing this as being in the form a over 1 minus r, which would equal the geometric series where I do a plus a times r plus a times r squared, etc. So that was really quick. Now, had I done long division, again, let's go take our original function. And long division, you're not going to choose, but I just want you to see it working. My original function was f of x is equal to 1 over 1 minus x. So I'm going to take 1 and divide it by 1 minus x. Well, when I do this, I'd get a 1, and then I'd multiply it in, and I'd get 1 minus x. Oops, I shouldn't have a bar there. I'd have a 1 minus x. When I subtract those, I'm going to get 0 minus a negative x, which is x. And then I'm going to take x and divide it by 1 and get an x. And when I multiply that back in, I get x minus x squared. And then when I subtract those levels, I'm just going to get x squared. And I'm going to divide again. And I'm going to keep, and notice I will generate that same series. So the question becomes, what is my interval of convergence? Well, in order for a geometric series to converge, the ratio, which in this case is x, has to be less than 1. So I would have negative 1 less than x is less than 1. And there's no sense to test those endpoints when it's geometric because we know it has to be strictly less than 1. If we did run our test, our ratio test on this, we would get divergence at 1 and at negative 1. And you can go check it, but you're going to get an oscillation and an nth term divergence. So anyway, I want to go graph this so you can understand what's going on with this. So I'm going to go down here. We're going to put a graph of this sucker down. So let's go see what we've got here. We've got 1 over 1 minus x, the original function. We've got our power series for that function, which we said was 1 times x to the nth, which equaled 1 plus x squared plus dot, dot, dot. And when I go graph these two functions, what you're going to notice, you already know there's an asymptote here at 1. So I'm going to go put an asymptote here. We know what the graph of 1 over x looks like. 1 over 1 minus x is just shifting that over. Here, let's go take the graphing calculator. I think I have mine up here so we can see it. So I'm going to go put both of those on a graphing calculator. So we have our original function, 1 over 1 minus x. And then we have our series, which was 1 plus x squared plus x cubed. I'm going to take it out a little ways so we can see it truly trying to wrap around that function. Notice I'm centered at 0, so I'm fine. If I centered at 1, I couldn't use this because I have there, but I'm good with my center over. So I'm going to go 1 more plus x to the 5th. Keep in mind the series would actually, the power series goes to infinity. So I'm going to take a look at my window here, and I think I'm going to go from negative 4 just to 4 by, oopsie, what do I got going here? Go to negative 4 to 4 by 1s, and likewise, and let's go see how, what is going on. I think I'm in the wrong mode on here. Nope, I'm good with that too. Let's try a zoom square. Go to still. I don't know what the deal is here. Oh, I have an extra parentheses. Oh, are you kidding me? Okay, so here we go. So there's the original function in blue. My Taylor series, 1 plus x squared plus x cubed plus x to the 4th, etc., is the red one. And you'll notice that between -1 and 1, I've got a really good fit. Actually, over here at -4, it's horrible, right? But if I wanted to improve it, all I would have to do is do the same problem, but center it at -4. You see, that's the importance of that center. I centered it at 0, and within 1 unit of 0, I've got a perfect fit. And again, this fit of the red to the blue isn't quite perfect because I didn't go to infinity. Every time, though, I add a degree to my power series, and I'm just going to second insert an x to the 6th right at the front of this. But every time I add a degree, that curve gets wrapped around there much more tightly. And between -1 and 1, it's actually a perfect fit. So there's my original 1 over 1 minus x with the asymptote at 1, and my power series 1 plus x plus x. Notice adding that degree just changed the end behavior, but again, in my interval of convergence, my power series and my function are exact. So let's go a little faster on the next one here. So it says find a power series for 1 over 1 plus x. What I really want to do is I want to recognize that I can manipulate this into geometric form. Geometric form is a, the first term, over 1 minus the common ratio. The 1 is important. You have to have a 1, and the minus is important. And so this one isn't quite there. So what I'm going to do is I'm going to go f of x is equal to 1 over 1 plus x. I'm good to go with the 1. I'm good to go with the a. All I'm going to do is rewrite the bottom as 1 minus negative x. Now I'm in what's called geometric form. I've got an a of 1, and I've got a common ratio of negative x. So the sum of this, right, we know how to do this. I can generate my series by saying it starts at 1, and then I keep multiplying by negative x. Then I'm going to multiply by negative x again, then by negative x again. And this would be the first 4 non-zero terms plus the general term. It's going to need an alternator. Let's make sure. I'm going to have to start this at n equals 0 to generate -1 to the 0. So I'm going to write n greater than or equal to 0 there, plus dot, dot, dot. So what I've just found is my first 4 non-zero terms, the general term, and the actual power series is the sum as n goes from 0 to infinity, -1 to the n, x to the n. Now, let's go see how good of a fit that is. Again, let's go graph this. My interval of convergence, by the way, for geometric series is where the absolute value of x, which is equal to x, is less than 1. So I'm on that same, and again, I don't really need to test those endpoints when I'm in geometric form, simply because we know that that ratio has to be between -1 and 1. But if I did on this one, I would have done my ratio test, and my ratio test would have said the limit as n approaches infinity. Again, you don't have to do this, but I want you to, this section's really good for everything coming together. This would have been x to the n plus 1 over x to the n. The alternator would have been killed off by the absolute value. I still would have had the absolute value of x less than 1. I still would have had my beefy wimpy, right, had I done this the long way. And when I put in a -1 up here, I would have had 1 to the nth, because the -1 and the -1 would have given me a +1, which diverges by the nth term test. And had I put a +1 in here, I would have had -1 to the nth, which diverges by oscillation. So, but for geometric, that's what's nice about it, is you don't have to go through that whole process. Now again, let's go take a look at the graph. What do I know about the graph of this one? It's going to have an asymptote at -1. Right? And I should have said about here was c equals 0. That was actually quite important. Let's go take a look at what my 2 look like this time. According to my calculations, 1 divided by 1 plus x was manipulated into a geometric series that started at 1 because of this, and then it had a common ratio, sorry, because of that, and then it had a common ratio of negative x, so it went minus x, and then times negative x again, and it goes plus x squared, then times negative x again, and it went minus x to the third, and then times negative x again, and it's plus x to the fourth, etc. I'm going to go one more, minus x to the fifth. And within the interval from negative 1 to 1, I should have a really good fit. So there's the original function, asymptote at negative 1. Coming in red here is going to be my power series, which will have, again, a really good fit between negative 1 and 1, and then it starts to diverge, and it diverges a lot. And if I wanted to have a tighter fit over here at 3, then I'd change my center to 3, and then I'd get some function that fits it nicely about that center within a certain interval of convergence. So I hope that helps tie it all together. Again, this problem could have been done two other ways. I could have simply done Taylor's rule on that, but simply is the wrong word for that because Taylor's rule can get kind of cumbersome when you're taking all those derivatives. This manipulating a geometric series is pretty slick. All right, so let's go take a look at another one. By the way, you usually look for this process when you have what we call a rational function. So I'm going to go circle this right here. This is called a rational function, and I'm going to call it R. A rational function is just the quotient of two polynomials. That's kind of important. I didn't stress that last year, and on their AP exam, it said to express something as a rational function, and they didn't quite know what that was. That just means as a ratio of two polynomials. So I'm doing the same thing here. I'm going to do my first 4 non-zero terms, my general term, and then I'll write the power series. If I were to do this with Taylor's rule, that would be a mess because my first derivative would require the quotient rule, and so would my second, and so would my third, and it would be very laborious. Long division actually is much quicker than Taylor's rule for ones like this, but it's awkward and people tend to make mistakes. So the best thing for this is going to be to manipulate it f of x equal x over 1 plus x into geometric form. And the sum of that would be a over 1 minus r. If I can get it into that form, then I can pluck off the a and multiply it consistently by r to create my geometric series. So I am fine up here with the x. That can be my a. A does not need to be a constant. It's just going to be the first term in the series. Sorry. This is a 1, which is super. This is not a minus. So I'm going to manipulate this one into geometric form. Now, what I'm going to do is call that f of x is equal to x over 1 minus negative x. If I wanted to, I could even pull this x out front and say it's x times 1 over 1 minus negative x. But either way, what's going to happen with this, and I want to put x over 1 plus x. What that means is my geometric series is going to start at x, because that's what this indicates. It indicates the very first term that's generated by some rule of sequence. So it starts at x, and every single time I'm going to be multiplying it by my common ratio, which is r. So I'm going to multiply this by negative x, then I'm going to multiply it by r again, then I'm going to multiply it by r again, and I have just generated the first 4 terms in the power series, plus dot, 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 the nth term, negative 1 to the n, x to the n, and I purposely made a mistake because I don't want you getting sloppy with those superscripts up there, because you've got to be very careful. If you want n to start at 1, so that can be x to the nth, and that would be x to the second, and x to the third, and x to the fourth. then this right here can't be an n because that'll generate a negative first term. So you'll have to accommodate that. If you're going to write it like this, you have to go and make that an n plus 1. So that when you start at 1, or even an n minus 1 would be fine too, either one of those will be fine so that you have the correct sign on the first term. Or if you want to start this at 0, what's also legal is for you to say it's negative 1 to the n. Negative 1 to the 0 will generate a 1, positive, but then it'll have to be raised to the n plus first power. All of those are good. What's not good is the first one that I wrote in red. I tend to like this because I like to start mine at 0. I like to be consistent. So my power series is from 0 to infinity, negative 1 to the n, x to the n plus 1. And then sometimes it's worth just running a few times through your indices here. At 0, will you generate this first term? It'd be negative 1 to the 0, which is 1, times x to the first, which is perfect. When I go to 1, I'll get negative 1 to the first, which will create this minus, and then x to the second, and I'm well on my way. So I now have my first 4 terms of the power series, my nth term, and then the actual power series itself, just for vocabulary. Now again, I could have done this with Taylor's rule. Taylor's rule would have said f of c plus f prime of c times x minus c over 1 factorial plus f double prime at 0 times x minus 0 to the second over 2 factorial plus blah, 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 blah. I could have done that, but it would have been kind of a pain in the butt with this. I'd had to use the quotient rule, as I said, with all these. Long division actually would have been nicer. Watch that. Nobody ever thinks of that, but it works kind of nice. If I were to say, oh, sorry, I have that backwards. No wonder it wasn't working. See, that's the problem with long division. You make mistakes. If I were to go like this, I'd say an x, and there's my x. See, it matches. And then I'd have an x plus x squared. And when I subtract them, I'm going to get a negative x squared. And then again, when I divide this by this, I get a minus x squared. Then when I multiply it back in, I get minus x squared minus x cubed. When I subtract the levels, I get 0 minus negative x cubed is a positive x cubed. And you can just you can keep on working your way on down. You're going to generate that same power series. This is awkward. Tend to make mistakes. Taylor's rule, all the derivatives gets lengthy. So it really is to your advantage to recognize series that can be put in geometric form. And again, you're trying to get them in the form a over 1 minus r. So you can start your series at a and multiply consistently by r, and it creates your power series. And we'll continue with that tomorrow. Your only homework is to show me these notes. Peace out. I am done.